Good morning. Today's class is the first of synthesis, truly synthesis classes. Okay. Heterocyclic synthesis can be divided in many different classes, subclasses, but what I have done, I have structured the course in a fashion where first I will talk about the 5 membered heterocycles and then obviously the 6 membered, and then if time permits then we talk about the fused ones, fused heterocycles like say Pyrrole-Pyridine or Furanopyridine, those sort of things. Okay. Then that means the first class which I have titled is the Pyrrole 1, in which we will be talking about only the Pyrrole synthesis, and Pyrrole synthesis is such a vast area, it can be divided into actually two classes, it could be even more, but I have restricted to only 2 classes. And in this one what I will do, I will select some of the important Pyrrole syntheses and then talk about one by one. The most conventional ones would be talked little later. Like many of you know, in case of Pyrrole synthesis there are 3 well studied or rather well known synthesis. One is Paul Knott synthesis, Knott synthesis and hand synthesis. So, we will be talking about those little later, and then among the 5 membered, let us say Pyrrole, Pyridine, Pyrrole, Furan and thiophene, many of you know the Pyrrole is actually more abundant both in nature as well as synthetic materials. So, there are, if you go through the literature, you will find almost every year there is a new synthesis coming up. Okay. And it is a versatile area, and a lot of people are innovating a lot of methods. So, but if you go to a recent review in chemical review by Gevorgen, one scientist name was Gevorgen, and he has written an article of 130 pages only on heterocyclic synthesis and with more than 800 references. So, it is very difficult actually to keep track of all these developments. Okay. So, what we will do? We will do these basic ones, the ones which are more frequently used in organic chemistry. Okay. And just let us look at the complexity of the synthesis actually. The first one, if you look at the Pyrrole nucleus and try to construct a Pyrrole nucleus or a substitute nucleus. So, where do you start from? Traditionally, and there are 2 ways to start from. Okay. What are the 2 ways? Number 1 is retrosynthesis, right, all of because we have been trying to organize any kind of synthesis by retrosynthesis. The other way, these are the 2 ways where to start. Let us say I give you an unknown problem and I say that okay, you synthesize this molecule, then you have to start your thinking. Okay. There are 2 ways, one is retrosynthesis, other is, which one is the other? Other best possible or rather best possible is the transform base. So, transform base because if I just try to show you the retrosynthesis is not really that is easy, and most often the practicing scientist what would do, they go by the transform. Initially they will do the retrosynthesis, but when they get lost they will try to do synthesis. But I will, let us say just very briefly, how many ways can you retrosynthesize your Pyrrole nucleus? Guess? No, how many? I mean, just give me a number that I can break this nucleus in 5 different ways, 3 different ways, 10 different ways, 20 different ways. Give me a number. That means what I am trying to say that retrosynthesis is very complex, very complex. If you any idea how many ways? Actually, I have a note. I will just show you. I do not know whether you can see it or not. This is 18, right? 18 different weight, but I can write more. So, that means we are lost. So, which one to, I mean for example, but if you have attended my synthesis class, if you remember, but my first clue about the retrosynthesis is anybody remember hydrolytic cleavages. So, what do? You just choose any one bond, especially the one that is attached to a heteroatom, just hydrolyze it. That means, at one point you have to add hydrogen, other point you have to add OH, result would be and then of course, the cleavage, and so then you have to have a little bit of this idea about this electronegativity. For example, when I write the first step, right, hydrogen can go to this nitrogen as well as carbon, but all of us know nitrogen is more electronegative. So, it will pick up this hydrogen. So, that means then we now restrict this choice to just one, this hydrogen should be on this side and OH should be other side. So, you break the bond here, right, and the rest remains as it is. So, let us talk about one more. Again, if you do so, what you will see, again you have one heteroatom, all of us know these enols they rapidly isomerizes to the aldehyde. So, we will not touch that, and then you have one more here bond, carbon nitrogen bond. So, we will break them, and then what about the hydrogen we had, we will keep them, then the new hydrogen should be placed and then new OH should be placed here. No OH should be placed here. Now, all of us know this tautomerism, and what you will find? You will find that it is nothing but succinaldehyde, right. So, this is one of the best way of looking at the retrosynthesis. Instead of going through all possible, say in a nucleus, let us say how do I generate all this, first you go by the number of the bonds. For example, I can clip one bond here, then second bond here, third bond, fourth bond, fifth bond, so like this number of bonds. Then what you can do, you can have a simultaneous cleavages, means at a point you can clip both the bonds together, then 3 bonds together, 4 bonds together, all possible combinations. Then there are two more important ones are like you can have a ring expansion. Let us say if you have to make a 5-membered ring. So, you start from 4-membered ring or 3-membered ring, then expand the ring system, okay. Ring contraction, that is also pretty popular way of making the Pyrrole ring systems. If you have a pyridine nucleus, you can just contract it and there are ways. So, you can make the Pyrrole ring systems. So, there are ways, I mean not only this I mean typical bond cleavages, this thing that thing you can, but I think the best way to look at the retrosynthesis of the heterocycle is the way that hydrolytic cleavages. Next thing that one should think about hydrolytic cleavages plus isomerization. Isomerization of the normally isomerization of the functional groups or the double bonds. This is one of these ways to look at, and the third one or the vice versa, isomerization followed by hydrolysis or hydrolysis followed by isomerization. This is one of these. Third could be general kind of the transform is the redox. That means either you oxidize or reduce all these things, okay. But these are if you want to go by these retrosynthesis, they are very broad. Now, if you go to the transform based, I think we have already talked about, right. The conventional ones is Paul-Knorr, and the next one is probably Knorr, and third one is Hunt's, right, Hunt's thing. These are the 3 conventional ones, and the latest one I think we will start from here from the 4th one, then we will go back if the time permits. The first this is a very useful one, this is called Barton-Zard reaction, Barton-Zard reactions, Barton-Zard reaction, and then there is one called Van Leusen pyrrole synthesis. Likewise there are many more. I think maybe one should also know Piloty-Robinson synthesis, Piloty-Robinson synthesis, Piloty-Robinson synthesis. There are many more. I think again depending on the time, maybe we will talk about little bit of this Huisgen. Huisgen synthesis, then we have Huisgen synthesis, then there are many others. I think maybe we will these are little bit of the specialized ones. Siba scientist at Singapore, and then there are many you can go on. I mean, I have selected only those which are really popular, and this is my prediction, though it may not be true, but I have added this one Jana. Jana is actually is from Jadavpur University, Umasis Jana. I do not know whether you have heard of him or not. He has published a paper in 2011. If the time permits, you should talk about that, you should learn about it. It is a very unique synthesis, though. It has been published in JOC, and it is likely to be a well cited method. So, if the time permits, we will talk about this. But as a whole, what I say is, I mean, the most successful approach, if you see, if we classify by the number of the atoms, first one is basically this 4-1 kind of cyclization. 4-1 means you have a 4 atom species and 1 atom species, like the Paul-Knorr one. This is the most successful one, and then this other successful one, of course, 3 plus 2, 3 plus 2, 3 plus 2. Okay. So, these are the two. I mean, so you can think about, I mean, there are all possible ways of looking at retrosynthesis, but when it comes to Pyrrole, you can concentrate on these two numbers, 4 plus 1 and 3 plus 2. When it 4 plus 1 means Paul-Knorr, 3 plus 2 means Knorr and Hans, even Barton, Van Leusen, all these are basically. Then Piloty is little different, Huisgen is again 3 plus 2, Siva again 3 plus 2, Jana is different, is 1 plus 1 plus 1 plus 1. Okay. He has combined all these chemicals together, as you will see, and then put little bit of the ferric chloride, nothing else, very unique. He has 4 different starting metal, and has just added 10% ferric chloride, and refluxed, he got all well substituted pyrroles, well defined pyrroles. We will talk about that. Okay. And let us begin with Barton-Zard reaction. Okay. So, when I say so, many of you know what Barton is, right? Who is Barton? He is a Nobel laureate. He died only 10 years ago from England. D.H. R. Barton, he has produced very well known scientist. Zard is Samir Zard is one of his students. So, what he has developed, once again, when I talk about a new synthesis of Pyrrole, you have to keep it in mind either 4 plus 1 or 3 plus 2, that is mostly, of course, and this is basically belongs to 3 plus 2. So, when I say 3 plus 2, that means you have to think about 3 atom component and 2 atom component. Okay, 2 atom component. In his case, 2 atom component is, that is what you have to remember. In his case, 2 atom component is a nitroalkene. Okay, that means these two are the contributing atom. The other one, obviously, if it should be CNC component. That means, when I say C, this is actually CC component, 2 atom, and the other component is CNC. That is what you have to say. That means, you have to choose a starting material where it will provide a carbon followed by nitrogen followed by carbon, and that is the trick there. And in his case, it is this C actually comes from isocyanide, and the third one is comes from this acetic acid group, and the starting material is is this one. I guess you understand what it is. It is ethyl isocyanoacetate, ethyl isocyanoacetate. It is not a cyanide, isocyanide. Okay. And isocyanate, again very briefly I can tell you how to make it, very easy to make. You start from glycine hydrochloride, okay, then boil with methyl formate, it gives the N formylation. If time permits, I will give you the reaction, and then do the dehydration. The dehydration, there are about 10 different ways, but the most commonly used method is POCl3 and triethylamine. So, that is very easy to make, anyone can make it. So, that means the starting material is only this one, this nitroalkenes. Any case, then if you use a base, obviously the most commonly used base is little strong base is required, potassium tertiary butoxide. All of you can guess what happens. So, actually base has a function to deprotonate of the most acidic hydrogen. In this case, the acidic hydrogen that would be picked up is the one between ester and the isocyanide group, and then all of us know that Michael addition reaction is one of the fastest reaction. So, it will undergo Michael addition. What does it do? It creates a new carbon ion. So, eventually what will have now, so it is a new bond here, and then C, right, N, and this is a carbon here and this is minus, and many of you know, I think the way one should write this isocyanide, it is basically a plus, carbon means it is a plus center and a minus center, right. So, this plus and minus forms a bond here. Mistake? Yes, there is a mistake, right. There is a mistake, actually this should be ester. Okay. Then what? So, now we have a 5 membered ring, C double bond N, this is the ester here, R1, R2, right. Now, the negative charge is here, and here also you have to have a nitro group here, the nitro group here, right. What next you can think of? It is an exchange, carbon ion deprotonation, intramolecular deprotonation. So, or intramolecular, so the deprotonation would take place, that means this here this hydrogen would be coming and the anion would be forming here, right. Anion would be forming here, CO2 and R2 and NO2. Okay. So, next there is, I mean, all kinds of the deprotonation would be taking place, and eventually there would be a loss of nitrous acid. So, eventually what you will be getting, I mean, you can do all kinds of these isomerization, all these steps, and eventually you will get the loss of okay, NO2 minus and R1 and R2. So, what you see here, there are things to be remembered. What is this? I mean, what is new here? New here, isocyanide is taking plus into the 3+2 cycloaddition reactions, okay. And then this what else interesting here, rather what else you have to remember? Often we do not see loss of NO2. NO2 is often is an activating group, it activates the alpha position, right, assists the or rather increase the acidity of the alpha hydrogen, but in this case it is basically activating a double bond, that means making a olefin as Michael acceptor, at the same time the NO2 also serving as a leaving group, that is what you have to remember. Okay. And this reaction is very useful, and the last step is abbreviated. I mean, you can do all kinds of proton dislocation and elimination on all these things. And now what else, just we will see an example, I mean how powerful this synthesis is. If you look at a target molecule, for example, in this case the target molecule is once again a pyrrole here, then I will write just simply R, in this R equal to here is benzyl in this particular example, then and you have 2 carbon and acetate here let us say. And now if you are given a synthesis or synthetic problem of this kind, so first thing you recognize that it has a pyrrole nucleus, then you think about there are ways. If you do not, you have forgotten the reactions, then you try to develop your own retrosynthesis. If you remember something about this, then you go by these, let us say as I said 4 plus 1 or 4 plus 2, but 4 plus 1 you have to remember 4 plus 1 is little more restricted towards 2,5 disubstituted pyrroles, especially when you have heavily substituted small one is very good. So, that is a transform based approach. Okay. The other one what you see, just if you go back to the earlier slide, you will see Barton gives what, mainly 3,4, because your nitroalkene has a substituent that would be giving the substituent at the 3 and 4 positions. So, we see that structural features here, and also the isocyanide, if you recall the Barton reactions, that it provides carbon nitrogen carbon. So, that means at some point you have to have a nitroalkene here. So, that means the nitroalkene that has to be that is to be made is some kind of right this one, then you have acetate. So, you have this methyl here nitro, and then nothing else, this is your isocyanide, ethyl isocyanide, or in this case is this one, that is it, and this is isocyanide. So, that means it boils down to the preparation of a nitroalkene, methyl nitroalkene. Okay. So, what is this? Now you need a base. In the previous example, I gave you a base tertiary butoxide. Now I give you a base that this is also possible with DBU as a base. That means you do not have to have an inorganic base, organic base is sufficiently okay. Okay. Now this one, nice. Now nitroalkene. How do we make nitroalkene? Those who are familiar with the very nice reaction though, or again a known reaction starts with H. Okay. So, what you have to do? You have to make a compound of this kind, then you have to have a leaving group here somewhere, and in this case the leaving group is this, mind it, and you have two, then we have one more acetate here, Okay. So, how do you make this? What is the critical bond you make? This one. Okay. So, then if you have a substrate of this kind, let us say the beta acetoxy nitro compound. So, in the presence of base, and again the base is nothing but DBU. So, you can have a E1 Cb kind of reactions, that means hydrogen is picked up, nitro is alpha hydrogen of nitro compounds is very acidic, I mean almost as acidic as aldehydes, okay, even more acidic. So, it loses, acetate group and eventually you get to this one. But how do you get this nitroacetate compounds? There is a reaction, many of you know, there is a reaction known as nobody, okay, Henry reaction. Have you heard of Henry reaction? It is nothing but it is an aldol condensation of nitro compounds, and in this case what do you do? You take this nitro and then react this with acetaldehyde, that is it. Once again in the presence of base, and what is the base here? The base is DBU. So, DBU is serving lot of purposes and right. So, this is equivalent to what? When you do this reaction actually, so what you will have, this is nitro and in this case it will have basically aldol condensation. So, in aldol condensation two components are the aldehydes or ketones, but in this case one of them is aldehyde, other is the nitro compound, okay. And this is OAC. So, that means after this aldol you get this one, then actually you have to use a reagent, this acetic anhydride, to activate the OH group to make it a better leaving group. And how do you do? Acetic anhydride and then what else? Pyridine, that is the commonest one, but also you have to know in this case if you do use pyridine it might lead to many things, because you know that it can also straight away give you the corresponding nitroolefin and other things. Okay. So, you have to restrict this, that means the by a new choice acetic anhydride and sulfuric acid. This is I think most often not talked about, but this is one of the nicest way of doing it. What do you do in case of acetic anhydride pyridine? You activate the OH groups, right, with the loss of hydrogen etc., but by using sulfuric acid actually you are activating the acetic anhydride. So, sulfuric acid proton protonates the acetyl carbon oxygen and makes the formation of acetyl cation easier. Okay. So, this is there are two ways one can make. So, that means that eventually it gives this one, but then what next? How to make this? How to make this one? Okay. I mean basically when I talk about synthesis, at the end of the synthesis you have to re-evaluate your synthesis on the basis of availability of the starting material. This is the most actually, I mean we often ignore this aspect in synthesis, but that is the most important aspect of synthesis. That means you have to make use of easily available starting material. In that case the synthesis should be the better one. When I talked about that Jana's Pyrrole synthesis, what he has done, he has taken all these readily available starting materials. Okay. Then he used a reaction that is enough to give you a particular molecule. Okay. So, you have to keep it in mind, your starting material should be readily available, easily available. Okay. So, to make this one, so one can think about what is it? It is basically a 3 carbon aldehyde and a nitro compound, 3 carbon aldehyde and a nitro compound. So, how do you get it? So, it is an alcohol, right. So, I mean now one can reduce this, we can reduce this with how do you reduce chemoselectively this aldehyde group keeping the nitro intact. NPV I have no idea whether it works or not, but any other suggestion? You have two reducible groups, nitro and aldehyde, and diol possibly would work, but again not readily available though. You have to have a cheaper starting reagent. Okay. In this case it is boron dimethyl sulphate complex, boron dimethyl sulphate complex. Of course, next step is acetic anhydride, and acid. This okay. Boron dimethyl sulphate complex is discovered by H. C. Brown and IIT KGPN, right. I told you in the fourth year class. Who was he? Arun Kumar Mandal, MSc from IIT Kharagpur KGP in 1971. Okay. And but next thing, we are still one step away from the completion of the synthesis. Okay. How do we make this easily available, this nitroaldehyde from a very easily available starting material? Okay. Without wasting time, let us see. Yes, acrolein readily available, commercially available, but what do you do? But you have to choose the other starting material, other reactant. So simple, right? Only thing you have to add, that means as if you have to do a little bit of the Michael addition. Michael addition where nitro NO2 minus would be serving as the Michael donor, and nothing, and you will not believe the reaction is so simple. You take sodium nitrite and acetic acid, nothing else. The reaction is very simple. That means sodium nitrite also can undergo Michael addition to acrolein. Okay. So, as a whole you see here the synthesis of the pyrrole has been eased by the use of Barton-Zard reaction. Okay. Let us look at one more reaction. This is also a very powerful reaction, So, the next one we talk about is Van Leusen Pyrrole synthesis. This is a very is very similar though. It is again the mode is 3+2. And very similar. So, like the previous one, what you need is a double bond, activated double bond. So, it has to be alpha beta unsaturated, something like this, right. So, in the previous case also, but you had a nitro group here in the place of acetyl group. Then the other one again a CNC fragment, carbon nitrogen carbon fragment. What is it? That means here nitrogen here, and I think the way I have written it seems like it is an isocyanate, and then this is the trick, and Van Leusen probably, I am not sure, I think is an Israeli scientist, I am not sure. Okay. Now, what do he see here? What is it? This is tosyl group, and this is CH2 group, methyl and isocyanate. So, this is known as popularly known as, you will find anywhere, tosmic, tosyl methyl isocyanate. What is it? It is equivalent to CNC fragment, is equivalent to a CNC fragment like the one before, right. And if you use sodium hydride in this case, what is expected? That this hydrogen that is activated, that methylene hydrogen, and would be deprotonated with sodium hydride. Then same old thing, Michael addition taking place. So, you will be getting a new carbon ion, that means and I will just write tosyl group, now you have a carbon ion here, right, and isocyanide means plus and minus. So, it will form a new bond here and this. So, it is a 5 membered ring now. Now, this carbon is minus, right, and here you have this tosylate here. Okay. So, then you can go on, it will you will have olefin here, and this is nitrogen. At some point it will be like this, tosyl here, this is hydrogen, and then I mean so on. You can just basically lose the minus what methyl, then this is benzene, and what you will be getting? You will be getting this minus methyl, this is phenyl sulfinate, this is sulfinate not sulfone, sulfinate, and then isomerization etcetera. Eventually, you will get, if you do the isomerization, you will get this pyrrole here, I think, oh, there is a methyl group here and a methyl group here. Okay, that is it. So, it is very similar to very similar to the one the Barton and Zard reaction. What is the difference? Difference is that the CNC component carries the leaving group, in this case tosyl group. In the previous one was the nitro group, and this nitro group that was in the two atom component, but in this case the leaving group is in 3 atom component, and in the place of nitro it is the sulfone. Okay. And this is a very nice way of doing it, and the outcome is very similar to Barton-Zard reactions. What you see here, that you are getting a 3,4 disubstituted pyrrole ring system. Okay. And something little more, not heterocycle, this compound is very useful, tosmic. I do not know whether you know or not. In general, it is a very useful compound in carbon chemistry. Let us say if you have a ketone of this kind and you try to do the homologation and put a cyanide here, how do you do? This is actually known as Van Leusen reaction. The previous one is called Van Leusen Pyrrole synthesis. In this case, this is known as Van Leusen reaction. This is a very simple trick, just basically you are adding a carbon, mind it. You started with an isocyanide and you are ending up in the cyanide, and all these things are going away, including your methyl that methylene group etcetera etcetera. Okay. And is nothing but tosmic, and I think DME is a solvent in this case, dimethoxy, ethane and potassium tertiary butoxide. It is a very useful reactions. You want to add a carbon onto the nitrogen carbonyl group, and this is one of the ways of to make it. Okay. So, let us see, that means both the reactions are very similar. Now, let us look at one more reaction, that what I said, this was done by Jana, and what he has done, you will see, I mean it is pretty interesting. I mean all kinds of the starting metals we think about in learning in organic chemistry, aldehyde, and then okay, I think I will make it acetyl acetone. What else? One more thing. So, it is a 4 component reaction, there is 4 different starting material, and the reaction is done in one part. and this nitro compound. So, the previous two syntheses also were involved in nitro compound, and this one, and the ferric chloride only 10%, 10 mole percent of the starting materials, and the net result is in just reflux, by the way, just a reflux, no solvent. I think nitro compound is given a large excess, little excess. What you get, this is this one, and sorry, this is R1, sorry, R1, and this is R3, and this is R2, this is R2, this is R1. You see here, I mean it supersedes all these pyrrole synthesis, and he has made some more than 20-30 different pyrroles by this method. And the trick is very similar. What is the trick? Again, you can just classify this method into 3+2 systems, although officially it looks a little more complicated, but it is basically, when I say that means to memorize this reaction, if you consider this as a 3+2 reaction, then it is pretty easy. So, how do you get this 3+2, and what are the first reactions you can think of? Let us say first reaction you think of, if you have a 4 component reactions of like these, I mean you have to just mentally make up your mind to decide which one of the is the fastest reaction. Normally, if you have an amine and alcohol, aldehyde, the Schiff's base formation is okay, but that too again in equilibrium. That means often the Schiff's bases are in equilibrium with the aldehydes and the ketones. Okay. So, you have to have a reaction which will be irreversible, and the best irreversible is the reaction that is your Henry reaction. Henry reaction means the reactions with the aldehydes and the nitro compounds. So, aldehydes and the nitro compounds, that means that would produce what? R3 and right, is not it? It is just like aldol condensation. This aldehyde and the nitro compound would be producing this, like let us say if you take benzaldehyde for example, to just refresh your mind, take benzaldehyde and nitromethane, and in presence of base, I think this is HS, right. It gives you nitrostyrene. It is very easy to make. It is described in Vogel's book. Nice green compound, You can make it in one day without any problem. So, that means this is a must first reactions. Okay. What next? So, we have seen that these two would be reacting, obviously then the other two are left out, right. So, amine and a beta ketodiketone, 1,3-diketone. What is the reaction? Anybody can guess? Anybody can guess? The way I have written here, I can write beta ketodiketone is a very fast reaction. You can do in just half an hour's time. Take acetylacetone, all of you have handled at some point. Take acetylacetone, dissolve in ether, add little bit of aqueous ammonia. What do you guess? Close, inaminoketone. Very easy. Just take it in a separate funnel and just extract it. You check the NMR, you will see what it is. That is nothing but this is inaminoketone, and in this case is this one. That is it. So, if you have, and what else? What is the next step? That enamine, all of us know, is a nucleophile. So, and nitroalkene is an acceptor, Michael acceptor. So, eventually what you will be getting here R1, I mean you can do all kinds of the other mechanism, do this one, R2, in this case R3, and this is nitro and this is hydrogen, right. What else? That means the molecular addition taking place, all these things, then again isomerization, they all these things, eventually you get basically addition of the two components. What next you can expect? What next you can expect? What next? Nitrogen will attack? Right. So, that means you have to decide, actually in this case this nitro also is a good leaving group, that is we have been seeing that, right. So, we will be getting this nitro and this is R3, this is R1, R2, this is R1, then you have everything here. What next? This is a sort of aerial oxidation kind of things. So, dehydrogenations. So, dehydrogenation will give rise to this one, give rise to this dehydrogenation, loss of hydrogen which is an oxidation, and that will give this one. Okay. So, it is a very good reaction, actually there are examples of these kinds, I will not go to these, we will quickly look at one more reaction, and this reaction is known as Piloty-Robinson reaction, Piloty-Robinson reaction. What it is? Piloty-Robinson reaction. Okay. Piloty, of course, he published these reactions in around 1910, and then there is a person, this is one of the very few ladies though. If you are interested in lady scientists discovering organic reactions, you have to go to accounts of chemical research, and I went to that article, and then I eventually found that this Robinson is not the true Nobel laureate Robinson. Have you heard of Robinson before? Robinson, his wife actually, he is not the Robinson himself, Robinson's wife. Okay. And that article actually describes that she is one of the very few lady discoverers of organic reactions. Okay. Actually the reaction was discovered long back, and the original one is nothing but, if you take hydrazine for example, hydrazine and let us take a ketone, what do you expect? So, if you have, let us say you have a ketone and of this kind, take the hydrazine, condense, just heat it, heat them together, and what you will see? Condensation, if you get hydrazone, but many of you probably do not know, if the proportion is not really taken care of, actually you get dihydrazone. That means, you will be getting this kind of molecule, dihydrazone, and in fact it happened. We tried to make one the benzophenone hydrazone once upon a time, but we could see that both the nitrogens are condensed. Obviously, and this is quite obvious, right. Once it is condensed on the other side also, if the material is available. And what they did, the first two are just simply took HCl and heat, HCl and heat, and of course, the product is here, is this one, Pyrrole is Pyrrole. That is it. There are two things to be learned. It is very similar to, many of you know Fischer-Reynolds synthesis, right. It is very similar. In this case, what is happening here, you are getting this isomerization to enamine, right. This is well known, isomerization to enamine. Then I think all of you can, just by looking at the structure, you can make out what would be the next step. What would be the next step? Pretty easy. Very good. So, that is quite obvious, right. So, 3,3 sigma traffic, that means this bond would migrate. That means, so what you will be getting is this N, this is now NH, now again NH R 1. So, this is now we will have 3 sigma tropic R and R here and R prime. What next? Nitrogen will attack. That means, this nitrogen will attack. What we will get is imine, then this would be NH2 R here R prime R and R here, right. And R. Now, what is quite important here, this then goes to again enamine NH2 R prime R and in this case R double bond. What next? I think all of us know that this nitrogens, geminal nitrogens, they do not, these 2 nitrogens on the same carbons, okay, are not very comfortable. Okay. One of them has to lose, one of them has to depart the molecule, and so you basically you get a loss of ammonia. So, you go to this product that we have written before, and this is this one R and R, and what you see in the only striking thing about this, that reaction loses an ammonia. That means, loss of ammonia in heterocyclic chemistry is very commonly encountered. Okay. I mean, ammonia is not a good, NH2 is not a good leaving group, but when you have a driving force like aromatization of this kind, then you can expect a leaving group property of ammonia. There are other molecules. So, I mean this can be, in fact, very recently just in 2009 or so, there is a paper in Organic Letters, and what they have done, they have taken a very similar compound, but in this case the R, both the R primes are in a different phase on the one side, and both the R's are in other side, and the Bock derivative tertiary beta oxycarbonyl, and what you have to do, you have to take xylene, and then of course, xylene boiling point is around 140 degrees, and simply heat it, and you will be getting the corresponding Bock protected pyrrole. Mind it, in this case what you are losing is actually, you are not losing the ammonia, what you are losing Bock-amide. Okay. This so what is the merit of the synthesis? Now you see you have well defined dihydrogen, the previous one was symmetrical one, means all these R and R, the molecule is symmetrical, but in this case you can separately add 2 olefinic components by a reaction known as I think many of you have heard Buchwald amination. This is a very famous reaction now, Buchwald amination. It involves actually copper catalysts, So, if you start from an iodo compound and a hydrazine, Bock protected hydrazine, you can do this new carbon nitrogen bond. Okay. So, so likewise there are many more reactions, and I think summary what I said next class, what we will be talking about, we will be talking about how to convert this alkyne precursor to pyrrole synthesis, open chain compound with a triple bond, and next one more very famous style of making pyrrole molecules. Remember, anybody remembers? To start, when we started the lecture, we said that this pyrrole synthesis can be classified certain. Number one is the conventional ones, other is not so conventional like this, Barton-Zard, Van Leusen, maybe Jana, and this one Piloty-Robinson. There are many more. So, I have chosen this. Then other 2 categories of synthesis, that would involve basically transition metal catalyzed isomerization, cycloisomerizations. Yeah. Means you will have to have an alkynes or alkenes, and you have somewhere add a nitrogen, then you cyclize it. So, that mode is a very useful mode, we will talk about in the next class. And also there is a approach, there is an approach based on ring contraction. You take pyridazines, do the ring contractions, then you do have a pyridine molecule, N oxide etcetera, you can do photolytic ring contractions, all kinds. And the third one, one is a special one, that is starting from azido compounds, also very similar to these reactions, but in that case the starting material is azido compounds. Okay. So, we will talk about those in the next class.